All right, so far we have mostly focused on constructing these neural networks and gathering of information on different levels, basically constructing embeddings on different levels of graph. But we haven't looked at how now we have to train this model. So the only focus that we had was on the propagation rules. Now, what we want to do is to basically define different tasks on the graph and then say that how we can train different graph neural network models in order to perform different problems that we want, right? So to do that, we need to answer to two questions. So at the outer layer of our graph neural network, what we have is some embedding. It's either a node embedding, an edge embedding, or a graph embedding, which is output of some pooling, right? So first thing we need to answer is that how to turn these embeddings into predictions. Let's say that we have node embeddings. Now we want to predict the labels of that node. Let's say that we have graph embedding. Now we want to predict some classification or predict some property of that graph, right? So the second problem that we need to answer is that now we turn these embeddings into predictions. Now, how we can update our model. In order to do that, we need to define some loss function, some objective function. So we will look at how for different problems, we are going to define different loss functions. So we will start with the most encountered problem. Most popular problem, which is node classification. So for the problem of node classification, you're gonna, as input, have our node embeddings, our node embedding ZI, and then we're gonna use that in order to predict what category this node belongs to. So let's say that I have a fake versus real classification problem for a social network graph. Let's say that on Twitter, I would like to find if different users are fake users, are bots, or they are actual users. So what we want to do now is to take that node embedding, and we want to map that into one of two categories, fake or not fake. So another example we can look at is categorizing the topic of different, papers, given the words that are in those papers as node attributes, and given the citation network as the graph construction of how these different papers are connected to each other. So let's say that if you have written a paper in electrical engineering, there's a good chance that there are more papers on electrical engineering citing you. If you have written something on history, there's a better chance that history papers have cited you. So we can use this structure, we can leverage this structure in order to basically categorize our papers. So basically, we know some papers, what their labels are. We know the words that have been used in different papers, and then using those, we want to categorize this into different categories that we have. Let's say that's science, engineering, and humanitarian sciences. So for that, we're gonna take our node embeddings, and we're gonna use some linear mapping that maps these into some scores. So these scores are representing basically the likelihood of each paper, or basically each entity, each node of that to belong to each of those C categories, right? So for that, we need a W, that is D by C, where D is just a dimension of our embedding, C is the total number of the classes that are possible.
So for that example, categorizing papers into different topics, is that supervised task?
Civilized?
Supervised. Does it have a labels? Did you say it has labels?
So for a set of them, yes. I mean, in graphs, you will see why. It is tricky to call them supervised and unsupervised. They usually call them semi-supervised, because when you say supervised or unsupervised, you don't really have that structure, graph structure. So even for the nodes that you don't have labels, sometimes that graph structure is changing the basic story for you. So we have some nodes and we know their labels. And then those are our training points. We will go over that in basically a few slides from now. Basically, you can reiterate your question then after basically I described that.
So these labels are kind of made by human.
Yeah, so it's like, you know, you have 1,000 papers, you go over 10 of them, for instance, or 50 of them, and you say, you basically, as an expert, you know what the topics of these papers are, and then based off of those, based off of how these papers are citing each other, and based off of the keywords, for instance, used in these papers, you can basically categorize this problem. So, but there is more to than that to this, and you will see that in a few slides. So now let's say that we have our node embeddings. We have a basically linear layer that maps all these node embeddings into probability of belonging to different categories. And then now what we have is some score of that node belonging to different categories. And what we want to do is to turn those into vectors of probability. We want to see what's the probability of each node belonging to different categories. And we can do that by some normalization approach. So what we want to do is that our output, which output of our basically Z times W, which we are showing using white bar, should be basically between 0 and 1, each element in that. And then we want all of that to sum to 1. So we can do that using an approach, basically function called softmax. So we take our basically vector of scores, we use softmax to turn that vector into a vector of probability. Those basically each element is just showing you what's the probability of each node belonging to different categories. So for the category, for the research basically example, research papers, you just will have a vector that, for instance, you have 5 types of papers, and it's basically giving you the probability of that paper belonging to each of those 5 topics. Now, when you train your model, what you want to do is to maximize the probability of basically seeing observed data. So what you want to do is to use some sort of maximum likelihood estimation. You want to maximize the probability of the true incident. And the true incident is known using the training data. So you have a set of nodes for which you know the labels, and then you know the labels as a one-hot vector, meaning that, so let's say that we have 5 categories. It has all zeros except for one where it says that that's basically element is the actual basically category that our node belongs to. So let's say that I have engineering, I have medicine, I have social sciences, and I have, let's say, arts and sports maybe, right? So then if our true label is that it is an engineering paper, this is going to be 1, and this is going to be all zeros except for that. So this one hot vector, we're showing that as true label with y here. And we have some output y hat, which is representing our prediction, right? So we are going to multiply the probabilities to the element-wise to this one hot vector. So it is going to just give us the probability of the true label, the probability of the true category, right? So we're going to take that, and we're going to basically plug that here into our objective function. So we are going to minimize the log of this probability, right? So that will maximize the probability of this basically, this probability P. So now about the training data. So we looked at how our, we are training our model, but how we are using the data that we have. We typically have 3 sets of data in this node classification problem. Let's say that this is our graph. We have a set of nodes that we basically see their structure, their connections, and we see what their labels are. So these are our training nodes. The second set of nodes that we have are our test nodes that we are seeing at the same time. So we see some structure for this graph. We see that there are some nodes that have been citing other papers, but we don't know their labels. We call them transductive test nodes. Transductive meaning that they are seen during training, but their labels are not known. We also have a third set of nodes here, and that's called inductive test nodes. And these inductive test nodes are not seen during tests. So we see when we are training our model, we don't see these nodes, right? We don't see these are empty, we don't see their connections to any other paper. And you can think about it as papers that have not been published yet. So you're developing a model, you want to later on use, so for example, you're working for Google, you write an algorithm for Google Scholars, and then you don't want that to be just garbage whenever a new paper came up, right? You want to basically use that paper, basically model that you develop for, for a few basically years probably. So you want it to be able to handle new nodes that are added to our graph. And those are called inductive test nodes. So during training, we are gonna use basically propagate information over the labeled nodes. We are gonna use message passing, neural message passing. We're gonna perform basically neural message passing over the labeled nodes. Then we have some nodes for which we don't have labels, right? Just before that, we know the labels for this, so we're going to use them in computation of the loss function. So the second set is transductive test nodes. So these are seen on the graph, right? We know how they are connected. So these are incorporated during neural message passing. We find new embeddings for them, but we don't know the labels for these. So we don't use them in computing the loss. So the third basically set of nodes are not seen. We don't know their labels. We didn't even know they existed when we were doing our training. So these are neither used in propagating information when computing node embeddings, nor they're used to compute our loss.